Hi, my name is Lori Pratt. In this video, I'm going to review a decision model that's designed to help cable operators, or really any kind of telecommunications provider, to make some pretty complex decisions surrounding generating their own energy. This video was made as part of a joint project between Quintellia and Bloomberg. Now, in previous videos, we've looked at more general issues as to how cable operators, or again, other kinds of communication providers, might purchase their own renewable energy from different sources, and what some of the economic factors are that might mean that that's a good idea. This video is a little bit more specific. Here we're going to address what are some of the decision-making factors around energy generation. Specifically, let's imagine you're a cable operator and you have a particular head-end building with satellite dishes on the roof. Well, there's an argument that says it's a good idea to also put solar panels on the roof or build a wind farm nearby. So the real question is, what are the factors that are going to ultimately determine whether you will receive a return on your investment, and when can you expect to enjoy that return on investment? So we'll build this model up piece by piece. Overall, this is going to look complex by the time we've done, but each piece of the model is relatively simple. So I would advise you to hang in there. This is something that really anybody can understand if you just take it one piece at a time. So what this model starts out with is a calculator of the number of subscribers that are served at each head end. And the way we calculate this is we look at the number of homes that are passed at each head end, and then the percent penetration this year, here in 2013, and we just multiply those two numbers together. If we have 46% of the homes passed have purchased cable from us, then we multiply that 46% by the total number of homes passed to get the subscribers that are served per head end. Now that's at a starting point, and this simulation is going to run for 200 weeks starting in approximately the middle of 2013. Now at Bloomberg we have some projections that say that we expect the compound annual growth rate of subscribers to net out to about 25% over a 4-year period. So the first simulation I'll run here just really just shows how those subscribers grow. So what I'll do is I'll tell this to stop after week 200, and then we'll just run a little simulation that shows how the subscribers at a particular head end grow. In this view, you can see this is where we'll run the simulation, but you can also see exact numbers. And in particular, on average, our estimate is that there's about 400,000 homes passed per head end. Now, your numbers may be different here, and this model allows you to substitute in all of your own numbers, both in terms of base numbers, as well as you may have a different subscriber growth projection. So running the simulation, what you can see happening is the weeks are growing from 0 up to 200, and at the same time the subscribers per head end is growing based on that compound annual growth rate, and we've just plotted with this yellow curve the growth rate of this subscribers per head end number. So this part of the model calculates how much energy each subscriber of a cable system uses. Now, associated with a particular head end, we have those approximately 400,000 homes passed, which translates into a certain number of subscribers. And each subscriber is associated with equipment that's located at the head end, which serves their video and broadband and telephony needs. And there's also equipment at the hub, and there's also equipment at the node. And each group of equipment has a certain amount of power usage that grows on a per subscriber basis. And we'll look at those exact numbers in a minute. But very simply put, to get the total watts per subscriber in the first week of our simulation, we just add up the typical watts here in the middle of 2013 per subscriber at a head end, hub, and node. So really the question is, how is that number expected to grow going forward? And it's interesting, there's two kind of countervailing factors here. On the one hand, we anticipate that subscribers are going to become increasingly thirsty for power. This is driven by more video channels, greater demands on broadband bandwidth. We just believe that over the course of the 200 weeks of the simulation, the CPU load, just kind of the amount of compute power per subscribers, is going to grow, and that's captured here by this first week factor, and then we have a load that's our projection going forward after that first week. Now, interestingly, at the same time, the number of watts per performance, or the number of watts per CPU cycle, is actually going down. So equipment is getting greener. For a given amount of computational power, it's going to cost us less in terms of total watts. It's going to require less energy. So the question is, how do these two factors balance each other out? Are we going to end up having the per subscriber energy costs grow overall because of this first factor, or are they going to shrink overall because of the second factor? Well, the way the model works is it does that calculation and ultimately comes up with a kilowatt hours per subscriber on any particular given week. And let's run that simulation. So here's how those numbers work out. You can see that our estimate of the typical watts per subscriber per head end is 2.17. At each hub, each subscriber uses about 13.3 watts, and then the node impact is pretty small at 0.67. So by our estimates, the total watts per subscriber in the first week of this simulation is about 16. Again, your numbers may be different, and of course you'll want to substitute in your own estimates here as makes sense. Now the next thing we've done is we've said, let's call the CPU load per subscriber, whatever that is, in the first week of our simulation. We'll call that 1. And then we'll have a number that gets multiplied by such that that grows over time. And then similarly, the watts per CPU, call that 1, and that's this number that's going to decrease over time as, again, equipment gets greener, and so we can get more power for a smaller amount of energy. So we'll run the simulation, and we're going to see how many watts each subscriber consumes on a per week basis. And again, if you remember from when we were looking at the model design, the question is the fact that energy is getting greener going to mean that the watts per subscriber goes down, or is the fact that subscribers are getting thirstier for more compute power means the watts per subscriber goes up? So this simulation shows how all of those factors combine. And what you can see is, indeed, according to this simulation, the watts per subscriber are going down, and it's because of that greener energy factor that means that equipment is just getting cheaper to run on a per CPU cycle basis. So here's where we start to put all of these factors together. The first thing we do is put together the two graphs we looked at earlier, which is how do subscribers grow, and then how does the energy usage per subscriber grow also over time. And really those two factors are just going to give us the total required kilowatt hours per head end in a given week. So this is how much energy is required at a particular head end, whatever it's provided by, whether it's provided by solar arrays on the roof or wind farms or whatever else. And we can just look at the formula for that because it's really simple. It's the subscribers at the head end. And again, this is the subscribers associated with the head end, but of course also includes node and hub power requirements. So it's how many subscribers are being served this week multiplied by that kilowatt hours per subscriber this week. If you recall, we saw the second number was going down over time, but the first number was going up. So it's an interesting question. What happens when we multiply these two together? What's the joint impact? Now the other thing I have in this graph is, okay, if we know how many kilowatt hours we need to generate, how much is that going to cost if we buy all of that off of the grid? And we found a government source that contained some projections of grid energy charges going forward. And what you can see in this plot is for the next 200 weeks, starting around 2013, for going for about 4 years, all three scenarios that this government source analyzed give about the same curve. So what we did is we built a picture of that in a sketch graph, which is shaped like this, and this follows the shape of this government assessment for future projections of the cost of grid energy. Now it's interesting, I think it's worth pointing out that this is only a 4-year projection, but if you look at these curves, the real growth is going to happen after the 200-week period of our simulation. So if we can show that there's a benefit to solar even in this relatively flat period, then certainly that benefit to solar or other renewables is going to just continue to increase beyond the simulation period, which only goes through about 4 years after 2013, so through 2017, which is pretty early on this little graph. So let's take a look at what happens when we run a simulation of those numbers. You can see at the beginning of the simulation, the cents per kilowatt hours is 9.2. The energy cost for a typical head end, we estimated about $45,000. And then we have a certain number of kilowatt hours that are used at that head end. So the question is, what's going to happen as we run this simulation? So I've taken this energy cost this week. If all of the power for a particular, all the subscribers passed at a head end are supplied by grid power, and I'm going to be plotting that and running the simulation forward. And sure enough, energy costs are going to go up if we use 100% grid power. And keep in mind, this is a function of the subscribers going up, the energy per subscriber going up, as well as the cost on a per kilowatt hour basis of energy provided by a head end also increasing over time. So certainly straight grid power looks like it's going to increase considerably over the next few years, and this is really what's driving the analysis in this video. What can cable operators or other communication providers do about this? So this graph shows how everything fits together. The lever that we're looking at, the thing that's under the control of a cable operator or whatever company is looking to build renewables, is its investment in a transformation project in order to create the infrastructure to allow it to generate those renewables, whether it's building windmills or a hydroelectric facility, or, as we've been talking about, solar panels on the roof of a head end. Any one of those is going to be a project that has a particular per week cost. And so this graph here in the upper left is really the lever that we have available to us. And what you can see in this particular scenario is kind of a slow on-ramping of investment with after about a year, we start a really big solar investment, which then tails off pretty rapidly well before the 200 weeks. And why might we want to have this kind of delayed reaction or delayed transformation? Well, it's because we might have an idea that solar is getting cheaper, which it absolutely is. And so if we delay this investment, perhaps that means that solar panels will have a better business case and our ROI will be faster. But just to show you what we can do with this is we might change this envelope of investment to have a little bit more front-end investment. Obviously, this is going to produce different results. Obviously, this is going to produce different results than what we talked about a moment ago. Okay, so that's the first part of this model. So as we make that investment, that is going to just add up every week to this cumulative value, which is the total capital expenditure that we've made so far. Now, the next interesting thing, another of these curves that kind of works in concert with other curves, is, as we said, solar is going to get cheaper over time, so it might be a good idea to defer our investment in a program until things are cheap enough. On the other hand, you're losing the benefits of early operational expenditure savings, and so the question is, how do those two factors combine? Um, the other thing that's going on here is that typically we would finance this kind of a transformation project. And so as we pay down our principal, the operational expenditure as a percentage of your overall capital expenditure is going to decrease. So that also gets taken into account in the rest of the model. Bottom line, as we're building solar panels or putting up windmills or whatever it is we're doing, we have an ability every week to generate more wattage through this alternative source. And that wattage can be used to calculate the total kilowatts and the total kilowatt hours in a particular week. Now, that total kilowatt hours provided by alternative energy in a particular week, if you divide that by the total energy required at that site, you get this percent shift to solar capacity. And this will start out obviously at 0 and will gradually increase as more and more of these total kilowatt hours gets provided by some renewable source. So what are we trying to get to here? What we're really trying to calculate is the costs after a solar investment. And let's go to this financing model really quick to talk about that. Basically, for a given CapEx in solar transformation, this is going to lead to a particular level of debt. That's going to be based on the interest rate that we are able to service that debt at, and of course the period over which we're going to be amortizing that debt. So bottom line, this is going to give us a number, which is how much money do we need to pay every week to service the debt, the amount of money that we invested in the solar panels. And that's going to end up being an important part of the cost. And so you'll see that that goes into this diagram. So what we have here is this solar cap debt service, which is one of our costs. Another cost for the solar plan is every week we're still going to have to buy grid power because we don't have the entire head end, all of our subscribers powered with this renewable source. So we'll add that to this debt service cost. And then to keep the solar panels going, there's going to be an operational expenditure, to shovel snow off of them when it snows, and to maintain the inverters, and all of those operational expenditures are important costs to keep in mind. Obviously, we expect those to be much, much lower than the cost of kilowatt hours off of the grid, but it's still not zero. So these three factors add up to give us our weekly costs with solar, and I color-coded this to be yellow to stand for solar. And this is the bottom line. This is our takeaway, is how do our weekly costs, if we choose to have a particular solar plan, which we showed in this previous graph, our plan is represented by this investment in solar transformation. How do those costs to the business as a whole compare to the energy costs in a given week if we don't do any sort of transformation whatsoever and we stay 100% on the grid? So what I'm going to do is start the simulation. We'll get it set up here. So we'll take these weekly costs with solar. We're going to track that number. We're going to take the energy cost this week if we're on the grid. And, really the question is, which one of these is bigger? So I'll set up my simulation to stop after week 200 as we did before, and then we'll run this, and let's take a look at what happens. And what you can see is that the energy cost for the grid is really, really exploding, and the weekly costs with solar are remaining much, much lower. You can see 8 with 6 zeros after it, as opposed to this much higher cost given our current subscriber growth estimates. And so we see, at least with this model, a really huge difference in the energy costs if we're going to stay on grid power versus if we're going to go with solar. Now, just for fun, let's try changing that envelope, and let's say we don't invest in solar until a little bit later on. And the question is, how is that strategy going to change what happens within the simulation? So we'll just run that one to see the difference from one strategy to the next. And you can see qualitatively it's really similar. The grid costs are just really exploding compared to the weekly costs with solar, which are staying pretty low. So bottom line, alternative energy can save a lot of money operationally for a cable operator. Now your assumptions may vary and your projections may vary. And so of course, don't take our word for it. It's important to get your own numbers into a model like this. Furthermore, I think it's really important to point out that there are going to be different parameters for different locations. And just to kind of show you the beginnings of a multiple location model, any location is going to have a site survey that discloses how much sunshine there is there, hydroelectric there, is there wind there. I'm just starting to give a few examples. And for each one of those site characteristics, we'll consider a number of different choices. And so far we've just talked about solar. And each one of those choices, given a certain set of characteristics of the site, is going to lead to a different cost component as well as other benefits. So this isn't a fully built out model. It's just meant to be indicative of the direction that you need to take. So far we've shown how you can calculate, if you know you're going to go solar, what the cost will be. But there are other outcomes that we care about, our ability to do green marketing, our disaster resilience, and our choice of solar, hydroelectric, and wind might have different impacts on these three things that we're trying to achieve. But that all depends on the characteristics of the site. So different locations, bottom line, we might need to make different choices and we might have different benefits. This is a very site-specific kind of decision making. And so you'll need to build a model like what we've shown here, where we have this per week investment and transformation. That's going to need to be a site-specific transformation cost. Because different sites, the ideal envelope for that kind of investment will obviously be different as those site characteristics shift. Thank you for your time and attention today. Really appreciate you making it here to the end of what I hope was a valuable video with some useful insights. Again, I'm Lorian Pratt with Quantellia, and this project was done in collaboration with Bloomberg Broadband Advisory Services.